Okay, so we have to follow the rule that the lowest energy orbitals are going to get filled first when we're filling our electrons. And so this doesn't necessarily follow the shell level, unfortunately, because some of the d orbitals are going to be of lower energy than the higher shell level, or some of the higher shell s orbitals are going to be lower energy than our d orbitals, and they'll end up filling first. So on the periodic table, when we were talking about our shell numbers, again we have, shell 1, shell 2, shell 3, shell 4, shell 5, shell 6, and shell 7. And we said that our different shells can have these different amounts of orbitals. And so for each shell level, we can give those a symbol by designating the shell and the subshell. Let's take hydrogen, for example. Hydrogen, we know, has one proton because its atomic number is 1. Its weight, its atomic mass is also 1. So we know that this has one proton, one neutron, and it has one electron in its ground state. So this is how the atom of hydrogen is going to exist. And so we know that hydrogen is in the first period, which means it has this s subshell. So it has one orbital where that electron can be housed. So we could say that hydrogen has a 1s1 configuration for its electrons. So this one is stating the N number, this position states the L number, and this position up here states the number of electrons that are housed in that orbital system. Okay, so we can list this as 1s1. So if we look now at the next element in the periodic table is going to be helium. Helium has 2 protons. It also has a mass of 4, so we know that helium has 2 protons. It also has 2 neutrons because it's got a mass of 4, and 4 minus 2 is going to be 2. And in the ground state, it's also going to have 2 electrons because that atom has to be neutral. So the number of electrons has to be equivalent to the number of protons. So when we're positioning those 2 electrons, we're going to say that it still is in the 1 level. So the N number has to be 1. We know that in the first level there's only an s orbital, and the s orbital can house 2 electrons within that orbital. So the electron configuration for helium, we would say, is 1s2. So when we move up and we look at the next element, we could say lithium is the next element. We see lithium has 3 protons. It has a mass of 6.94, so that's close to 7. So the major isotope of lithium is going to have 4 neutrons, and it's going to have 3 electrons. So because it's going to balance out, and those have to be equivalent. So 3 protons and 3 electrons in the ground state. So we now know that lithium is up in level 2. So it has both the first subshell, and it now has a second subshell. So for lithium, the electron configurations, the ones at the very center, are the lowest energy, and so these guys have to fill up first. So we have to put 2 of the electrons in that first subshell, in that first level in the s subshell. Now we can move to the second level. In the second level, we have the option of the s and the p orbitals. The s orbitals are lower energy, and so they are going to fill first. And so there's only 1 electron left because we only have 3 electrons in this atom. So for the electron configuration for lithium is going to be 1s2, 2s1. So those are the designations or the addresses for where the electrons are going to be housed within this element or this atom. So now what we need to do is we need to really look in depth at these different orbitals and their energy levels, because it just isn't straightforward. We don't just go, necessarily. The p orbitals for the second level would be the next lowest energy orbitals, and they would get filled. But when we get to the third subshell, it gets a little bit more complex because these d subshells are actually higher energy than the next level s orbitals. And so the filling pattern becomes a little bit strange after the third level. We can easily draw a structure to get the energy orbitals and their filling diagrams. And it kind of looks like playing solitaire. So if we list out our subshells, we can start this one. So if we list out our shells, we can just go right across the top and we can say 1, 2, 3, 4, 5, 6, 7. So we want our ends coming across this way. And that's like our first layer of our solitaire that we're laying out here. So we know that the first level only contains the S. So we're going to put that in there. And in fact, every level contains an S. So we can put the S's all the way across on the top level. On the next level, we're going to put the p orbitals in. The first shell has no p orbitals, so we can skip that one. The second shell has p orbitals, so we'll put those guys in. The third also has p. The fourth has a p orbital system. All of the rest have p orbital systems, so we can put those in next. The next level is going to be the d orbitals, so we know that the second shell does not have d orbitals because it's too small. The third, though, does, so we can put those in, and then everything above that has the d orbitals. So we can add those, oops, that should be 5, 6d, and 7d. And then finally, the f orbitals would come next. So we know our third level does not have the f orbitals because it's not large enough. But then our fourth and beyond has the f orbitals, so we can put those in as well. So we would have a 4f, a 5f, a 6f, and a 7f. And now to get the energy filling diagrams, we just draw diagonal lines in here. So if we draw our diagonals going up, we're going to come back and then go up again. So we would see the 1s fills first, now the 2s, this is going to come back down. Now we're going to have the 2p, the 3s, and then when we come back down and draw our next diagonal, this is where it gets a little weird. So now we're going to have the 1s fills first, the 2s fills next, the 2p would fill next, the 3s would fill next, the 3p would fill next. But now instead of filling the 3d, we're going to fill the 4s first. The 4s would fill next. And then we're going to come back around. And we're going to go in this direction with this diagonal. So next the 3d would fill. Then the 4p. And before any of the remaining levels of the fourth layer can fill, the 5s orbitals are lower energy, and so the 5s would fill. We come back down and do our next diagonal, and we would see our next diagonal comes up this way. So after the 5s fills, our 4d shell would fill, and then the 5p, and then the 6s would end up filling, and now we would come back down. And now you would fill up the 4f. So if we continued filling apartment buildings, 4f would fill, 5d, 6p, 7s, and then we would come back down here, the 5f, the 6d, and the 7p would fill. We come back down again, the 6f, the 7d would fill, and then finally the last subshells that would fill would be the 7f orbitals. So this is the lowest energy filling that you could possibly have. And we could go through and we could put how many electrons could be housed in each one of these orbitals. And so we can write that very easily as well. Make sure they're all on the diagram there. So our s orbitals can only hold 2 electrons. So these could be a possibility of having 2. The p orbitals can hold 6. The s's again can hold 2. P's can hold 6. 2. Our d orbitals can hold 10 because there's 5 orbitals in that subshell. The p orbitals can hold 6. The s subshell is 2. The d subshell 10. P is 6. 2. Now we get to our first f subshell. This can house 14. It's a big apartment building. The d can hold 10. The p can hold 6. The f can hold 2. The s can hold 2. The f can hold 14. D can hold 10. P can hold 6. The f, again 14. The d, 10. And the last f, 14. So there's a maximum number of electrons that can be housed within the electron orbitals or within those shell layers. And then past this point, the atom becomes too big and it's too unstable, it won't exist. In fact, most of these really heavy elements don't exist in nature. They're only created in the lab, and they're very, very unstable and break down very, very quickly because these conditions out here where you're filling just the f and the d orbitals at the very end are really unstable, and they don't like to retain this composition. Okay, so if we added all these up, so there is a possible of housing 158 electrons around a single atom. That would be our heaviest element that we could have possible, and we have not found such an element. So this one seems to be too unstable to exist on the Earth. But that would be our prediction, that we could have an atom that could house that many electrons based on the number of electron shells that are possible.